hFE, often written as beta, is the DC current gain of a bipolar junction transistor in a common emitter configuration. It tells you how much the transistor will amplify a small current applied to its base. The H stands for hybrid parameter, F stands for forward current amplification, and E stands for common emitter. Mathematically, it is the ratio of the collector current to the base current. hFE is equal to IC by IB. For example, if a transistor has an hFE of 100, feeding a 1 milliampere into the base will allow 100 milliampere to flow through the collector. When building transceiver circuits or linear amplifiers, matching the hFE of discrete transistors is especially critical for push-pull amplifier stages to ensure the signal amplifies symmetrically without introducing distortion. Here is a BJT hFE simulator. The base hFE rating shown here is 100 and base current is 500 microamperes and emitter current is 50.5 milliampere. That is, this one is added to this one. That is, collector current is 50 mA. And if you increase the base current, keeping the hFE rating fixed, that means for the given transistor, collector current gradually increases. And when it reaches 1 milliampere or 1000 microamperes, the collector current is 100 milliamperes. This is for the same transistor with the hFE rating fixed. Suppose you change for a higher rating BJT, you can see what happens. As you increase this, there is a massive increase in collector current. With a 300 hFE rating transistor, that should be a different transistor, not the same transistor. The same 1 milliampere current will give 300 milliamperes of collector current. Correspondingly, this also changes, that is emitter current. Emitter current will be the sum of these two currents. Collector current and base current together will be the emitter current. So this is an interesting demo or simulation of what happens with, you can go it the other way around also. So 0, very little amplification. Low hFE occurs beyond the transition frequency. When you go for higher frequencies like radio frequency, there is something known as transition frequency. At transition frequency, hFE will be 1. So minimal gain will be there, and actually no gain, because when hFE is 1, there won't be any gain. Here the minimum hFE shown is 10. Testing a transistor's hFE allows you to verify it is functioning properly or to sort a batch of transistors to find identical pairs. There are 3 common ways to measure it at the workbench. Using a digital multimeter. Most standard multimeters have a dedicated setting and socket for this. Turn your multimeter dial to the hFE position. Determine if your transistor is NPN or PNP and look up its pinout in a data sheet to identify the emitter, base and collector. Push the transistor legs into the corresponding E, B and C slots on the multimeter's circular testing socket. The screen will display the DC current gain directly. Digital multimeters usually test at a very low base current, so the reading might differ slightly from data sheet maximums. Homebrewers, that is do-it-yourself group, and electronics hobbyists, cheap multifunction testers like the popular LCR-T4 graphical testers are incredibly convenient. You simply lock the transistor's 3 legs into any 3 slots of the 0 insertion force socket. Press the test button. The device automatically detects whether it's an NPN or PNP, identifies the pinout and displays the hFE along with the forward voltage drop on the screen. Breadboard method. If you need to measure hFE at a specific operating current, which is useful for calibrating bias in RF power amplifiers, you can build a simple test circuit. Connect the emitter to the ground, apply a known voltage through a known high value resistor to the base to supply a specific base current, apply a supply voltage to the collector through a load resistor, measure the actual current flowing into the base, then measure the current flowing into the collector. Divide the collector current by the base current to calculate the exact hFE for those specific conditions.